Nanotechnology, Free University of Bozen-Bolzano, Italy. Dr. Cantarella received his B.Sc in Information and Communication Technology Engineering from Politecnico di Torino in 2011, and M.Sc in Nanotechnology for ICTs from Politecnico di Torino, INP Grenoble, France, and Ecole Polytechnique Federale deLausanne, EPFL, Switzerland in 2013. He obtained his Ph.D. in Electrical Engineering from ETH Zurich, Switzerland in 2018 with a thesis entitled Stretchable, Oxide, Semiconductor, Transistor, and Circuit. He was postdoctoral fellow at the Nanomaterial Engineering Research Group at ETH Zurich, Switzerland, and at the Sensing Technology Lab at the Free University of Bozen-Bolzano, Italy. In Feb 2020, he has been appointed Assistant Professor RTD-A at the Free University of Bozen-Bolzano, Italy. Now I'd like to invite our today's guest. Sir, please, now floor is yours. You can continue after sharing your slide. So you are not audible.
Can you hear me now?
Yes, yes.
Okay, that's great. Let me just share the screen. Hopefully it will be working. Okay, here it is. Can you see that in full screen now?
Yes, sir.
Okay, that's great. Okay, so first of all, thank you very much.
So
And
you can go to that display setting. Actually, we are getting next slide also in the comment window. It's not in complete full mode.
okay.
You can go to the display setting and make it duplicate.
Okay, this is okay. That's strange. It should be. This is with F5, I suppose. Is it better now?
No, sir. Still, it is in that mode only.
Okay. Let me just see this. Okay. Okay. Just give me one display settings. Okay. Duplicate. Okay. Sorry, it's taking some time. So maybe. Is it better now?
Yes, sir. Yes, sir.
Okay, so you can see everything, I suppose. Okay, I probably need to make this disappearing, right? Okay, I think now it's better.
Yes, sir.
Okay, great. Let me just put the pointer, so hopefully I would be, okay, that's great. So good morning or good afternoon, everybody, and welcome to this talk. Thank you very much for the introduction. And before starting, I would like to sincerely thank the Indian Institute of Technology, Indore, for the invitation, and clearly even the IEEE Nanotechnology Council for the invitation. So as already said, my name is Giuseppe Cantarella, and I'm working at the Free University of Bozen-Bolzano in Italy. The idea of my talk today is to kind of give you a broad overview of the work that I've been doing here since I joined this university 2 years ago, but also the past work that I've done during my previous academic career at ETH Zurich during my PhD and my postdoc. So as you all know, in the last 70 or 80 years, electronics has expanded towards a lot of different research direction. Two of them are the ones that you see here. So the number of integrated circuits, but also the portability. So in terms of number of integrated circuits, we all know that probably 60 or 70 years ago, you know, a computer, a very simple computer could probably needed the same space of a huge office, of a huge office environment. Whereas nowadays we have the opportunity to enjoy very lightweight and an easy and small laptop, in our office and in our daily life. In terms of portability, we know that the electronics is composed of usually bulky and heavy and really heavy components and system, for example, supercomputers or servers. But at the same time, we can also enjoy. We are now in the age of smart and portable devices, so smartphone and tablets that allow us to really have high computational power just in our hands and in our pocket. So the question and the topic that I've been working on since I would say almost 10 years was trying to envision, trying to understand how the electronics, the next generation of electronics could be and how it might look like. The answer that my colleagues and I are giving us is exactly to imagine electronics as you can see here. So electronics that could be realized on foils, on polymers, on rubbers, with the capability to be still functional when mechanical strain is applied. For mechanical strain, you will see that I mean, for example, bending, stretching, crumpling, so any sort of stress that, in standard case could damage, for example, a silicon-based electronics. So what are the features of this kind of electronics? Clearly, it can be extremely lightweight. So as you will see in a couple of minutes, the idea is to have electronics which could be realized on very thin and very conformable and flexible substrate. Conformable because the idea is that these electronics could be placed could be transferred on whatever kind of surface we want. So it could be a rough surface, it could be curvy. So any arbitrary shape according to the application. Clearly, also another aspect very important is the material science. So the analysis and the employment of materials that, for example, can make these electronics biocompatible for specific applications, as you will see in a couple of minutes. And clearly, last but not least, the flexibility. So having devices that could be still functional when mechanical strain is applied. So why people should work on flexible electronics? What's the idea? Well, clearly, since I would say 10 years, 15 years, people have been investigating on different research field. Try to imagine, for example, how could be embedding and integrating together textiles, so our clothes, with devices that can, for example, monitor the quality of our sport activity. So creating a new generation of textile that we can therefore call smart textiles. We can have, for example, electronic skins. So devices that are incredibly conformable to our skin and can, for example, help us in doing specific job duties that are impossible without the presence of sensor or electronics on top of our skin. Smart consumable electronics. There are already big companies such as LG or Samsung that since already years have started selling, for example, foldable smartphone or bendable display, which is clearly a very an high profit market. Very challenging, but still very promising is the field of biomedicine. So trying to see whether these electronics could, for example, be integrated with medical devices and can support, for example, physicians and doctors to monitor the quality and the health of patients. There are also wearables, so devices that can go in intimate touch with our skin and can monitor, for example, the quality of our vital signs, so blood pressure, blood oxygenation, heartbeat. There is also a very new, I would say, but fast growing application field that is the so-called smart farming. So agriculture that in which we can, for example, place this flexible electronics on the soil or on the leaf to monitor the quality of the plant during the growing phase. Last but not least, even the food industry. So having, for example, food tags or smart packaging that can tell us the quality of the food that reach our home, and trying to understand better the quality of drinks and food that it's reaching our table. So that's the outline of my talk. What I would like to do is introduce you to the materials and devices that have been implementing, and an overview of how we made electronics stretchable. How do we realize with the proper material selection, highly transparent and imperceptible devices? This is a work in which we try to aim on flexible, so bendable light emitting diodes, so LED. This is a very last topic, last results that we obtain here, in which we try to investigate on sustainable and circular electronics, and then just a conclusion to wrap up the talk. So let's start from the materials. So the most important thing when start working on this research field on flexible electronics is to identify a thin film technology, so a semiconductor that can help us in having functional devices on these polymeric and polymeric substrate and plastic foils. So what you see, for example, here is a series of different semiconductor groups or thin film technology represented as a function of the electrical mobility, electronic mobility. So you see, for example, the organics, metal oxide semiconductors, carbon nanotubes. This one is the transition metal dechalcogenates material. So for example, 2D materials. We have silicon crystal silicon and also 3-5 semiconductors. So there are a lot of different parameters that we need to take into account for the selection of the proper thin film technology. Clearly, the most important one, the first one that we need to care is the electrical properties, which means, for example, having semiconductors that can guarantee high mobility, that can guarantee also a very low threshold voltage to work on low voltage electronics. So for that reason, we didn't investigate, we didn't work on organics. Large area scalability. The idea is trying to make electronics that could be as big as possible. So device, circuits, chips, system that could be in the centimeter square, or in any case as big as possible. So for this reason, we had to not consider the 2D materials, which are still at their infancy stage from this point of view. Deposition temperature. Whenever we talk about flexible electronics, we always talk about a series of layers and materials that have to be deposited and fabricated on polymers, on plastic foils, so we never go at temperature above 400 degrees, for example. So clearly, this is an obstacle for the application of silicon and 3-5 semiconductors. Device type. We would like to make also as much as possible complementary devices. So we need a thin film technology where we might have N-type and P-type semiconductors. And that's the reason why we excluded carbon nanotubes, which are mostly P-type. And then the last parameter, which is pretty important, is the commercialization. So having a technology with a stability, that could be in the range of months or even better in years, to make sure that these electronics could be realized and have stable functionality over time. For this reason, we have been working on this class of semiconductors, these metal oxides, and you will see in a few minutes on which material specifically. So this is the typical output of our device, how our device would look like. So we work with bottom gate staggered transistors realized on flexible substrate, which is what you see here in light blue. More specifically, for substrate, we mostly use either rubbers. So what you see here, it's polydimethylsiloxane, so PDMS, which is a pretty common rubber in case of for example, stretchable application, but also we have been extensively working on polyamide foils, on plastic foil, which are 50 micrometer thick. Then comes the deposition and structuring of the gate metal. Usually we had the possibility to apply through vacuum-based processings, a lot of different materials according to the application. So from titanium, gold, chromium, copper, up to something more fancy, such as indium thin oxide in case, for example, of transparent application. Then afterwards, the dielectric. So we need to make sure to employ and use an insulator layer, which is very conformable and pinhole free. That's why we use aluminum oxide deposited by atomic layer deposition. The deposition of this layer is the highest deposition temperature that we employ in our fabrication, which is 150 degrees. And then comes the semiconductor. As I was saying before, we employ one material from the metal oxide semiconductor family. In particular, we use an alloy of indium, gallium, zinc oxide at the amorphous state, sputtered at room temperature by radio frequency. And the idea is that this semiconductor guarantees an N-type functionality. So most of our electronics is NMOS only, and guarantees a mobility around 15 centimeters square volt per second and threshold voltage below 1 volt. And then usually we conclude our fabrication with, the source and drain metal contact or interconnection in case of circuits, again with a broad range of applications and a broad range, of materials that we can employ. So the typical outcome of our fabrication is, for example, a foil like this one in the centimeter scale. This one is 7.5 by 7.5 centimeter, in which we are able to fabricate and characterize from very simple devices, components such as transistor, but we could even realize analog circuits, so mostly amplifiers, but also logic gates, which means, for example, not NAND, nor, so different logic gates. During the years, my colleagues and I have worked towards different applications. So, for example, as you can see here, the employment of stretchable rubbers as a substrate allow us to go towards stretchable applications. What you see here in the middle, imperceptible and unabrasive, consists in the employment of highly transparent materials. So we change our gates, our electronic stack in a way to achieve highly transparent applications and highly transparent electronics. Conformable electronics consists in having all the electronic stack, including the substrate, incredibly thin, sometimes even below 5 micrometer, to achieve a perfect conformability around any surface. We have been also working on complex system, which means the integration of our oxide technology, for example, with other technologies for the realization of complete system that can, detect data and communicate also the data, so also the processing of the data. We have been also working on high frequency, so try to make our transistor as fast as possible, considering also the material limitation that we have working with plastic substrate. So trying to achieve, for example, hundreds of megahertz. And last but not least, also trying to tackle large area circuits. Clearly, we are very far from what people nowadays, after 70 years of evolution, can do on silicon electronics. So we're not still integrated in billions of transistors, but considering the material limitation that we have, we achieved an integration of 30 or even more than 30 transistors for the realization of large area circuits in the range of millimeter square area. So one of the first questions that asked ourselves was, how stable are our transistors? So can we apply, or can we make sure that our electronics could be stable at any environmental condition? So the work, the result that you're gonna see, they are recent outcomes from a PhD student from Federica Catani in my group, that she investigate the performance variation under different environmental conditions. So what she did, as you can see on the left-hand side of the slide, is simulating the most extreme climate zone on our planet using a climate chamber. So what she did was simulating, for example, from very high temperature zones, such as, for example, the desert at 50 degrees with a humidity of 22%, down to the low temperature areas, such as the Antarctic, to minus 30 degrees and no humidity. And the idea was to monitor the performance of our transistor in this case. So what you see here is how the drain current of our transistor changes as a function of the gate source voltage. This one is for the cold areas, so everything below 18 degrees Celsius, and here is the variation instead for everything above um, 18 degrees Celsius. So what she also investigated on, in case for on-skin applications, was also to see, for example, how the electronics could change in terms of performance drift according to the proximity to our body. So she found out that our body has, let's say, three climate zones, three areas with different temperature. This is what you see here, the forehead, the arm, and the foot. And she analyzed what happens at this three temperature at three different humidity values. So here, for example, that's the forehead analysis at three humidity levels. That's the arm analysis, still again at three humidity values, and that's again the value for the foot, which is the lowest temperature of 29 degrees, still at three areas, three different humidity. So the idea was to make sure and evaluate and consider the performance drift in these specific environmental conditions. So this drives me already to the application of stretchable electronics. So whenever we talk about, most of the times people talk about flexible electronics, meaning electronics on plastic foils, which are therefore just bendable. If we would like to get stretchable devices capable to, for example, be twistable or stretchable or crumpled, definitely additional effort is required. So in a very easy way, the idea is that whenever we have a flexible substrate with some electronics fabricated on top, whenever we apply mechanical strain, any sort of mechanical strain, such as bending or stretching, what we are doing is creating a very high strain region at the interface between the substrate and the electronics. Starting from this consideration, we tackle this problem and we try to solve this using two approaches, the buckling approach and the engineered substrate. Let's start having a look on the buckling. As you can see here, the idea behind this was trying to create wrinkles, so out of plane wrinkles in the layers of my electronics, in a way that whenever I apply a certain mechanical strain, so for example bending or stretching, what I'm doing is not stressing the electronics, the device itself, but rather reflattening these wrinkles. So the way we achieved this was using a transfer release process. So what we did was using a silicon carrier wafer coated with a sacrificial layer. This is what you see in green. This is a water-soluble sacrificial layer. Then we use our rubber, so our stretchable substrate, and then we complete the electronics fabrication. Afterwards, when the fabrication is complete, what we do is to dissolve the sacrificial layer to disattach the PDMS from the carrier. So this is exactly what you see in this video. So in fast forwarding, what you see is the water that it's going underneath and is slowly dissolving the sacrificial layer. At the end, the result it's a floating substrate with the electronics on top. Clearly, The advantage is that after the dissolution, what happened at this stage here is that the elastomeric substrate release all the thermal stress, so it shrinks, creating these out-of-plane wrinkles that I was presenting before. And then, therefore, we can fish and place this elastomeric substrate anywhere on any arbitrary substrate. This has allowed us, for example, to realize the wrinkled electronics, so devices such as transistor, inverters, and NAND, clearly based on our IGZO semiconductor, so only N-type, with all these out-of-plane wrinkles to make the device sustain the mechanical strain. So from at the macro scale, what we have is exactly what I showed you before. So the idea is that we can fish this membrane with whatever arbitrary substrate. Here, for example, this is a plastic foil, but it could be even expanded towards other applications. So for example, what you see in this video is that this approach could be even used on leaf. So in case we would like to target, smart agriculture or smart farming, clearly these electronics could be easily placed or even on this kind of substrate. The second approach I wanted to show you is the so-called engineered substrate. So the way we tackled this was to think in a different way. So rather than using a flat substrate, we thought to create these pillars, these structures, as you can see here in this 3D rendered image, on top of which we can realize our electronics. So our aim was to realize a large area substrate in the centimeter scale, and then trying to place on each of these pillars some devices, for example, circuits, transistors, sensor, temperature sensor more specifically, trying to make sure that this could be functional even after any sort of mechanical strain. What you see here, for example, are finite element simulation that shows you that during a specific mechanical strain, such as bending or twisting, the strain experienced by the electronics on top of these pillars is almost zero. So it's very low. So what you see, for example, in this video are the way we realize our mechanical tests. So for example, this. Can you hear me? Yes. So I was just saying, these are just examples on how we realize our mechanical tests. So bending, for example, stretching or twisting using this engineered design. So what you see on the left-hand side is the 3D rendering, but on the right-hand side is the real image where we really realize electronics on top of this elastomeric stretchable substrate. And in this way, we could achieve, for example, functional transistors. So a transistor that have functionality up to 20% and then could be easily reflattened. What you see here is the transfer characteristic again. So how the drain current changes as a function of the gate voltage. Sorry, even circuits. So what you see in colored here is the output of an inverter circuits with functionality in the same way up to 20% and then reflatten. And then last but not least, thanks to a collaboration with the California Institute of Technology in US, we employed a natural-based material often present in plants, which is called pectin, which is temperature sensitive, to also realize stretchable temperature sensors. So as you can see here, within a range that goes from 40 degrees until 30 degrees, either in flat condition and in stretch condition, the performance of our sensor does not change sensibly. So imperceptible electronics, as I was saying before, a big portion of our job is also to investigate on materials and trying to see how some of this material can guide us towards specific application. In the case of imperceptible electronics, the main focus, the main idea is to achieve from the substrate up to all the device in the electronic stuff, highly transparency. The idea is, for example, to realize an abrasive devices and abrasive circuits that could go, for example, on skin. So for biomedical application, again, in case you would like to have devices not visible to human eye, clearly the use of highly transparent material is highly suggested. Another application could be, for example, automotive. So if we would like to equip the mirror of our cars with devices, with circuits, with display, clearly we also need to investigate on highly transparent devices. So using this approach, so the employment mostly of indium thin oxide as metal contact, we have showed, for example, highly transparent transistors. So what you see here is the transfer characteristics with a gate current that you see in black here, which is always below in the picoampere regime. And here it's the output characteristic, and you see that from 0 to 5 volt, our transistor have the capability to easily saturate. We also are investigating, there is a work, we're also writing this manuscript, we also investigate on transparent circuits. So more in details, we work, for example, on ring oscillators. This is the schematic of the circuits that we have been working on. So it's a series of 5 inverters, one connected to each other. Clearly, as I was saying before, our IGZO transistor are only N-type. So the P-type transistor in our case has been replaced by an N-type transistor in diode connected mode, which consists in having the gate connected to the drain. So here we have a 5-ring oscillators, a 5-stage ring oscillator. This is the output. So here you can clearly see the 5 inverters that I was meaning, plus the output buffer layer, and that's the output. So we have characterized this oscillator at different supply voltage, so a different VDD voltage. The idea, what I wanted to present here, is the fact that our circuits could go and could be still functional at very low voltage. So in particular here, we had working oscillators at a supply voltage as low as 1.745 volts, so below 2 volt, and still having a perfectly oscillating circuits. We have also investigated, as I told you, towards analog circuits. So the idea was to investigate, for example, common source amplifiers. Same style, we use a driver transistor, which is N-type, and for the load transistor, we use again an N-type transistor in diode connected mode. This is how our common source amplifier looks like, and these are the outputs. So what you see here, the colored in different colors, are the amplitude, so the output of our common source amplifier at different supply voltage. So in red you see the 2 volt, 4 volt, and 5 volt. Still, the idea was, the take-home message was to make sure that these electronics could be transparent, could be clearly flexible, but also make sure that it could be even functional at very low voltage, which is the case here. Again, a motivation to make these electronics unabrasive and highly transparent is what you see here. There are a lot of application in the biomedical field, so for wearables or imperceptible devices. So for example, these are devices that have been fabricated on PDMS substrate, and the use of indium thin oxide as metal contact, and then IGZO and aluminum oxide, which are already intrinsically transparent, give the result of a very imperceptible smart patch that could be placed on our body. Another application where such a kind of electronics could be very useful, for example, is smart farming, where you really need that the sunlight goes through any device, any patch that is placed on top of the leaf. Then we have been also working, investigating on light emitting diodes. So what you will see, the result that you will see here are the results from a collaboration with the Nanomaterials Engineering Research Group at ETH Zurich in Switzerland, led by Professor Shi. The idea here was to kind of trying to tackle the world of light emitting diodes, LED, which are a really important and basic component of our electronics. So we can find LED everywhere in our daily routine, and therefore the idea was trying to investigate how to make single devices flexible, clearly, but using a specific technology, a new technology that I'm sure you are familiar with, which are the perovskite-based electronics. So this perovskite, it's a new class of material emerging since, I would say, some years. And the idea is trying to see how this technology for LED could beat or could perform better with respect to other technologies such as quantum dots LED or such as quantum dots or organic based LED. Three ways to judge these are the technical features, so the results that we can get, the compatibility with respect to other technologies, so how easy or how difficult it is to combine perovskite LED with other thin film technology, and clearly if we would like to achieve the market, the cost per unit, so how much a single LED would be. So just going one by one, clearly there are advantages in using perovskite because they have a full width at a half maximum, as you can see here in this plot, which is as low as 20 nanometers, so much smaller than what could be achieved with other technology. And also the photoluminescence, the photoluminescence is above 93%. So clearly there is a great advantage in using this technology rather than others. Regarding the other two parameters that I was mentioning, so the compatibility and the cost per unit, the solution, the answer to that, it's just unique. It's one, and it's good for both because the fact that these materials could be spin coated, so using a very low cost methods make these perovskite materials highly compatible with other technology, but at the same time also very cheap in terms of production. So no need of vacuum-based and highly expensive machines. So the way we realize our flexible light-emitting diodes is starting with plastic foil, so either 50 micrometer of Kapton or 50 micrometer PET foils as a substrate. Then we proceed with the deposition of 120 nanometer of indium thin oxide as a transparent conductor. This was sputtered by radio frequency sputtering at room temperature. Then the LED fabrication start. We first spin coat as all injection layer 30 nanometer of P.PSS. Then we have as all transport layer 20 nanometer of poly-TPD. So again, as you can see here up to this point, everything could be easily spin coated. Then comes the emission layer, so the perovskite material, which is formamedium lead bromide. So as you will see in the next slide, is a layer which allows emission in the green regions, and even in this case, it's spin coated. Then as electron transport layer, we have 40 nanometer of 3PTY MB. And then to conclude the LED part, we have a very thin electron injection layer of lithium fluoride. And the last part is the second contact that we did it by evaporation with aluminum, with 100 nanometer of aluminum. The result, as you can see here, and that's what we aim for, were LED, so devices that could be even in the millimeter or even centimeter square area. So what you see here, for example, is an LED which is 5 millimeter by 5 millimeter. As I was saying before, is emitting in the green region, but we also went further up in terms of area and surface. And what you have here, it's a 2 centimeter by 1.5 centimeter LED, shining on a curvy surface. We performed the electrical characterization of the LED. So what we did is analyzing the current density and the luminescence as a function of the applied voltage. We also analyze the current efficiency and the power efficiency of our device as a function of the current density, so according also to the geometry and how big our LED were. And the photoluminescence intensity, which is also an advantage with respect to other technology, we compare it to, in colloidal solution, but also in film. And the good thing is that, you know, we can have pretty much the same performance at whatever state our perovskite layer is. The idea, as I was saying, is to realize flexible devices. So what you see here is the, you know, our device under a specific voltage from a radius of 3 centimeter down to a radius of 1.5 millimeter. Clearly, the lower the bending radius is, the more these black spots and therefore the failure mechanism occur in our LED. So you can immediately see this one here down to a bending radius of 1.5 millimeter. Our LED starts experiencing some failures, so the presence of this black spots start increase. What we also wanted to do, and that's the idea behind this video, was also trying to make sure that our large area LEDs, so the one in the centimeter square, could be still functional during a dynamic mechanical strain. So what you see is in a normal speed, the bending of a large area LED, the flickering that you see, it's due mostly by the non-ideal contact, metallic contact that we have. But in general, our devices are still perfectly functional. And what we did with this device was just testing for multiple times. So we did this bending down to 1 centimeter radius up to 5,000 times. And what we did was monitoring the efficiency, you know, up to this point. As you can see here, up to 1,000 cycles, there is the efficiency is pretty much stable, and it doesn't change. It's not affected too much after, you know, 4,000 cycles. So reaching this point, clearly due to the exposure with air and the absence of a passivation layer, there is a significant drop of almost 18% that clearly has to be tackled. Just to give you also an idea in terms of how the LED looks like when it's fresh and it starts this kind of test, you perfectly see that the LED is shining green, and the failure after 5,000 cycles are visible with these black lines visible here. We also went for passive metrics, so for systems considering an array of 7 by 7 arrays, and the result that you see here are the metrics, these passive arrays, both on glass substrate but also on flexible substrate. And the idea is that in principle, we could achieve up to an yield of 100%. So all the 49 LED were perfectly functional, and we could even selectively activate the line that we want. So this brings me to the green electronics. These are the latest results that my group and I achieved. And the idea was to investigate and make a step ahead towards electronics, which is not just flexible, but it could be even more environmentally friendly, which could be, more sustainable, considering also our environment. So the motivation, as you all know, I'm sure that you are all familiar with this table here. These are the 17 goals from the Agenda 2030 of the United Nations. And these are just some guidelines to, you know, live in a more sustainable way, but more importantly, provide a better planet and a better life to the new generations. So in our field, so even in our field, these goals have to be achieved. I mean, what you see here on the right hand side is how electronics is I would say a main source of waste. So it's very hard nowadays to completely recycle electronics, or the process takes takes a lot of time and it's very expensive. So it's very important, even from the electronic side, to investigate in this sense. I would say since some years, people are working on field of research, which is the so-called dissolvable or transient electronics, in which electronics is realized using green materials, and after usage, the electronics can be easily dissolved without leaving any harmful residuals. What we wanted to do in any case is to try to make a step ahead. So the motivation of our work was to see whether we can make the electronics completely sustainable and whether it could be reintroduced in nature after the usage. So what we did was starting our consideration from a raw material that is very common in our life, which are fruit leftover. And we just found out that there are companies realizing commercial papers using fruit leftover on one side and cellulose. So what we did was using commercially available papers based on kiwi, apple, and grape. These are the three foils that you see here in this picture. And the idea was to substitute any plastic foil, any polymer, with this absolutely natural and recycled material, which is, as I said, a mix between cellulose and fruit leftover. So the next step, let's say, in this circle, was trying to identify how we could use this paper as a substrate, but mainly how to realize electronics on top of the substrate. So we had to make sure that whatever process we employ, it has to be low cost, so energy affordable. We need to make sure that we could realize electronics in the centimeter scale, or even better in the meter square scale. We don't need to use any toxicants, so we would like to be as green as possible. And finally, the electronics has to be reliable and stable. So the approach that we use is a new technique, um, I would say developed in the last 5-6 years, which consists in the laser induction of specific substrate. So what you see here in this video in fast forwarding mode is that using a very common laser, a CO2 based laser, which is used, for example, in workshop to cut or engrave plastic or wood, we can just burn the topmost surface of our paper, and the result, which will be visible in few seconds, is a conductive carbon-based layer that could be employed for electronics devices. So this technique, as you can see, it's very easy, it's very low cost, because these laser systems are quite expensive, and we can employ even a substrate which could be even in the meter scale. So the result, as you can see here, for example, is the logo of our university, and this layer, these black metals, these black layers that you see, it's conductive carbon. Following this technique, people what have done is employing this technique for example, realizing acoustic transducers, so microphone-like devices. People have also investigated on the biorecognition, so trying to see whether this laser-induced approach can be used to realize biosensor and therefore understand the concentration of a specific analyte, but also to analyze simple strain sensor. As you can see here on the right hand side of the slide, the main idea, or what has been done so far, is to employ Kapton foils, polyamide foils, so plastic foils, which in any case are not as green as we imagine. So what we did is to analyze the network, our cellulose paper before decarbonization. So you see here there is a network of cellulose fibers which present also the typical leftover organic residuals of the fruit that I was mentioning before. Then after the carbonization under the microscope, the paper looks much more rough, and under scanning electron microscope, we can see this amorphous carbon that we can obtain here. Indeed, the results are also confirmed by Raman measurements that shows the typical D and G peaks on the apple substrate, the grape substrate that you see in blue, and also on the green, which is the kiwi substrate. And the results are large area devices that could be easily functional. So considering that we could have, for example, as I said before, conductive lines, the first device that came up to my mind, that came up to our mind was capacitors. So why don't we try to realize parallel plate capacitors burning the top and the bottom surface of the paper? And that's what we got here. So we got capacitances that are in the picofarad regime, according clearly to the area, and at the electric constant of the paper, which is as expected in the order of 2.4, 2.5 as a value as expected from the state of the art. We have also investigated on biosensors. So we use this typical 3 electrodes layout, and we compare the performances of our paper-based biosensor with a commercial biosensor based on carbon. And as you can see here, the current peaks are pretty much the same. We also went a step ahead, trying to see whether the biocompatibility of this paper could be even employed for on-skin application. So what we did is to compare, as you can see here in this image, the performances of the paper electrodes with standard ECG, so electrocardiograms electrodes, which are commercially available, and trying to see whether, for example, there are any performances drift between one or the other one. So on the left-hand side in orange, what you see is how we could monitor the heartbeat, so the heart activity, using a triplet of electrodes. So two located on the wrist, one here, and another one on the ankle. And you see that clearly with the commercial ECG, we get an higher amplitude, but with the paper one, we could easily identify the R and T peak and also the heartbeat. So the heart rhythm is perfectly equal as the one that we can get with commercial electrodes. Even for the respiration, so we kind of monitor whether with this paper we could, for example, monitor the inspiration and expiration. And as you can see here, all the amplitude, all the positive amplitude represented an inspiration, and all the negative amplitude that were representing expiration. And this was based on the change of the impedance of our lungs, so considering the presence or not of air inside. So following still the circle, we ended up in this point here in which our electronics could be functional using this approach. We thought, would it be possible to make these electronics dissolvable? So after usage, just dissolved it. So this is what we did. So we take a lemon juice solution, so mostly citric acid, and 2 small electrodes, paper-based electrodes, and we monitor what was going on at different, let's say, days. As you can see here, day 27, what we experience is that the cellulose is highly damaged and is almost gone. And then at day 33, and then finally at day 40, even the carbon part, so the carbonized part, is completely gone. So as you can see here, in 4 weeks, the cellulose is almost gone, and after almost 6 weeks, there are no residuals of our devices. We also collect the resistance of this electrode as a function of days, and apart from this peak here, which was due to damage of the contact, the resistance was pretty much constant until 27 days, which means that these electrodes could be even, for example, be used in outdoor activities and be still functional for different weeks. So we showed that our electronics could be even dissolvable and transient. So the second question, just to complete the circle, was, would it be possible to reintroduce the electronics, to throw it away in nature and try to see whether it could be functional? So what we did, that was a very simple experiment that I'm sure that most of us have performed at least once during childhood, which consists in taking a specific substrate. In our case is a carbonized um, sample with a very simple RC circuit, so one resistance and two capacitors. And what we did is performing the so-called germination test, which means placing some natural seed, these are tomato seed, on top of the paper and on top of the carbonized part, to see whether our electronics can become a support to make the plants and the seed growing. And after 72 hours, what you can see here, so feeding the seed with a bit of water, the result is that we already can see a start of the growing phase of seed. So in principle, after our electronics is used. So at the end of its lifetime, we can just crumple it, throw it away in nature, and we're sure to create a positive impact on nature, so on our ecosystem. So this is the full circular path that I wanted to show you and I introduce you. This drives me already to the conclusion. I hope that I'm not running too fast or too late according to the time plan. So as I said before, the idea, I'm trying to convince you that the way we see electronics in the next generation is flexible, biocompatible, sustainable. Clearly, we know that there are still efforts that have to be done in this direction, in the sense that we need to aim for high performance electronics, and this is a duty that has to be performed by electrical engineers, physicists, chemists. So there are a lot of, I would say, different topics that have to converge together to achieve or to improve the electronics, the performances of this kind of electronics. Clearly, considering our age and considering how sustainability is a key factor in our cities, in our countries, and in general in the world, we also need to pay attention and keep an eye open on how to make these electronics sustainable, green, and environmentally friendly. Innovative application, we need to make sure, or we need to tackle all those applications, all those technical problems in which our standard based electronics, so our phone, our laptop, cannot guarantee functionality. So we always need to envision and see how these flexible electronics can have an important contact point with the issues that we have in our daily life. And last but not least, even the commercialization. So we need to make also this technology stable enough to reach the real market, so real market scenarios. That said, I would like to thank my faculty and the province of Bolzano, Bozen, for the financial support, all the collaborators which have worked with me and are still collaborating with me for all the results that you have seen. Before concluding, I would like very briefly to introduce, our university and our group. So for those of you who don't know, as I was saying, I'm an assistant professor here in this little city in the north of Italy, which is at the border with Austria. Our university is located in two main campuses, the one in downtown where, the Faculty of Science and Technology is, but we also have equipment and facilities in this new technological park where research centers, so research institution, public research institution, research groups from the university and startup work together side by side in a very nice and incredibly high tech environment. So you are all welcome, you know, to come and visit us if you want. We have facility and equipment in both campus. In terms of facility, as I was saying, the idea of our group is to really work from the material up to the device fabrication, and then finally the electrical characterization or mechanical characterization at the end. So we have all is needed for the fabrication of the devices, either with printing technology or based on microfabrication technology. We have quite some material, quite some equipment for the chemical, mechanical, and surface and optical analysis of materials, and clearly a set of tools for the device characterization, so either electrical or mechanical. My group, the Electronic Materials and Device Systems group, is a very young group. Together with my colleague, Professor Nico Munzendider, we are just growing this group. It was just created 2 years ago, but now we already 8 people. So we have 2 postdoc, we have 4 PhD students, and we are still looking for other candidates who would like to join us and would like to work in this research field. That said, thank you very much for the attention. I'm sorry if I'm running too late maybe, and I'm open to answer all your questions. Thank you very much.
Thank you so much, Dr. Giuseppe. Now, for such a wonderful talk. Now, floor is open for question and answer session. Participant, you can unmute yourself and ask question if you have.
I'm trying my best to kind of go in the normal mode. You see, you still see my screen, right? Oop, sorry. Is here. Okay. So you still see my screen?
Yes, yes.
Okay, okay.
Good afternoon, Professor Giuseppe.
Good afternoon. Hi.
I'm Pawan Kumar from IIT Indore, and I have one question regarding like that. For example, if you deposit I-Z thin film on the silicon substrate and also flexible substrate, any changes and any improvement in the electron mobility and transconductance after using the flexible substrate?
So just to get this point, you are asking whether we notice any difference in the performances, whether our semiconductor is deposited on rigid substrate or on
Yes.
flexible, right?
Yes.
Well, that's the idea. I mean, the way we developed this technology was to make sure that you know, the performances doesn't change independently on the substrate. So let me just show you this. I hope this is still visible. So you still see my screen, right?
Yes, sir.
Okay, exactly. So sorry for the messes here. It's just a series of animation. The idea is that we develop all the different steps of our fabrication using, let's say, either UV photolithography or vacuum-based process. And the idea was to kind of use a temperature, but also chemistry in general. So solvents, base, and acids, which could be compatible clearly with substrate, but also with the flexible substrate that we used. So in principle, what we did, or the technology that we developed, considering the chemicals that we use, considering the temperature, the maximum temperature that we use, as a perfect compatibility with any arbitrary substrate.
Okay, sir.
I hope this was the answer to your
Yeah,
question.
yes, sir. Yes, sir. Thank you, sir.
In your lab, do you have a pattern generator for the microfabrication?
Sorry?
pattern generator.
The patterned,
Pattern generator to prepare the mask.
I'm sorry, I cannot get the question. Say it again, please.
Is there a pattern generator to make the masks in your microfabrication?
So you mean patterning, so structuring?
Yes.
Yes, absolutely. The idea is that every time, this is probably not perfectly visible from this image here, but maybe it is here. So what we do is to pattern is that we pattern everything with UV photolithography. So the idea is that each layer that I presented to you, from the gate metal up to the last metal, or the passivation, it depends on the specific sample, they are all patterned with UV photolithography and then etched by wet etching. So we don't use dry etching. And with this approach, we usually achieved roughly a resolution, so the distance between our source and drain of 3 microns. So in case of high frequency, high speed electronics, with standard UV photolithography, we could achieve, I would say, roughly 3 or 2 micrometer. So with the standard mask aligner, because there are problems due to the stability of our substrate. So with temperature or with the use of chemicals, we always experience a swallowing or expansion of our plastic foils. So 3 micrometer is what we can guarantee in this sense. We have also investigated, I haven't presented this, but we have also investigated on techniques to even further shrink this resolution. So what we did, and it's also something that we are still performing, for example, using FIB, so focus ion beam, we also try to reach the nanometer scale. So what we did in the past, and what we will also do in the next months, is trying to have a transistor on polyamide foils, on plastic foils, with resolution, so spacing between the source and drain, which are as low as 100 nanometer. But this is clearly, for that kind of application, we need new machines, but the standard protocol, the one that I presented here, is mostly UV photolithography and wet etching. I hope that was the answer to your question.
Okay.
Professor Cantarella, we have few questions in chat box.
Sure, sure.
From
Let me check the chat. Sorry.
From Srinivasan, should I tell the question in behalf of these
Maybe
participants?
no. I think it's fine. It's the one when using, right?
Yes, sir. It's to
Okay.
everyone.
When you. Yes, very good question. So when using flexible substrate, what are the key parameters should be considered to obtain high quality thin film transistor? That's a very good point. What we usually do, I mean, as I said before, what we do in our labs with my colleagues is that we really start from the materials analysis, then we proceed with the device fabrication, and then we go ahead up to the end with the characterization of the devices. So if we just look at the for example, the transistor, so the basic electronic component that we deal with, the parameters that we usually look at are, for example, the mobility that we can extract. So we know that, for example, our transistor, our semiconductors usually can have a mobility that goes between 15 and 20 centimeters square volt per second. We also measure and evaluate the threshold voltage, so the voltage at which let's say the transistor turns on, and we have the experience that for our thin film technology, you know, this number usually is in between 0.2 volt and 0.7 volt, roughly. Another parameter still on the electrical side that we care, for example, is the ratio between the ion-I-off ratio. Let me just show you an example so we can have a clear picture of what I mean. So here, for example, I hope my slide, that the slide number 17 is visible. The ion-I-off ratio means, for example, the difference between the current in the on state, which, for example, in this case is close to 10 to the fourth, and here, which is close to 10 to the minus 11. So this ratio here, just to prove that there is a very good modulation of the devices. Another parameter that could be very important is, for example, what you see here, the gate current. So the gate current is the current that you have, you know, passing through the aluminum oxide in our case. So it's the current that goes from the gate here, for example, through the dielectric and reach the source. And clearly, this current has to be as low as possible. So even in this case, considering our expertise, we are working with this technology since years, I would say even more than 10 years. We know that, for example, the aluminum oxide that we deposit guarantees a gate current that usually is in the picoampere. Which is, sorry, let me just get again that slide. Exactly. So this is, for example, what you see here. So everything in the range of few picoampere. So if we just look at the electrical characteristics, the electrical performance, these are, for example, the ones that I would say clearly there is also the subthreshold swing. So how fast, you know, the transistor can turn on and off. These are the standard DC parameters that we look at. So if we would like to have an analysis of the electrical performances, there are clearly also the AC parameters. There is clearly also the optical visualization. So step by step during the fabrication, you need to make sure that there are no dirties, there are no residuals or leftover that clearly at the end of the fabrication can cause problem to your devices.
Few more questions are there in chat box. Thank you, sir, for
Yes,
that.
yes. I suppose that's the one. Yes. So high quality. So what are the different types of piezo-resistive materials to be used in flexible substrate? This is a very good question. I mean, in our case, I suppose we haven't worked with piezo-resistive materials because in our case, what we were mostly interested, for example, were exactly for electronic purpose. So sometimes we were kind of we investigated on, for example, temperature sensitive materials. So in case of the realization of temperature sensors, we wanted to aim for highly temperature sensitive materials. So in that case, for example, we aim for example, platinum. But in this case, we don't have so much experience in that sense for piezo-resistive materials. Then there is also another question. In the fabrication of the perovskite LED, many steps are done using spin coating, but after one layer is deposited using spin coating and dried, the next deposition could damage the previous layer. It might be due to the same solvent. How do you take care of this? This is a very good question. I mean, as I said, let me just see here. Yes. So the way we realized the perovskite LED was mostly done by these collaborators that we had at ETH Zurich. I suppose that you know, the way the spin coatings are done are clearly managed in a way to reduce any damage to the successive layers. So for example, the P.PSS, I've been also working with this material, and usually as long as you spin coat it and then you dry it, you remove the solvent, you know, the layer, it's quite uniform and stable. Clearly, you need to make sure, so whenever you prepare the solution for, in this case, this old transport layer, you need to make sure that the solvent that you use doesn't harm the underneath layer. So it's just, I would say, chemistry that could be optimized, but for my experience, you know, all these layers and the solvents which are mixed up with are pretty stable. So the key aspect is to make sure to have in mind your device stuck and, you know, not employed solvents that can damage the layers underneath. So this is my suggestion in this case. I don't know whether there was another one. Yes. Oh, that's a very good one. What are all the low-cost fabrication methods we can go for flexible sensor without using clean room facilities? That's a very good point. I mean, as I said, there are a lot of technologies around that are you know, based on vacuum process or not. What I experience with my colleagues in general is that, you know, even if you don't have a clean room facility, most of these tools can work even in a normal environment condition. Just to give you an idea, let me just go back here. So, for example, our semiconductor. So, as I said before, the semiconductor that we use, our IGZO, is sputtered by radio frequency at room temperature. There was a moment, you know, during our group history that this sputtering tool was located in the clean room, but then afterwards it was moved, you know, in a normal office environment, in a normal lab environment, and we didn't experience any significant change in the performances. So that means that at least for this kind of application, this type of electronics, we didn't experience any, I would say, any significant change in the performances. So in principle, at least for the semiconductor, we were not bonded to the presence of clean room. Clearly, you know, there are a lot of all the structuring methods, all the technology that we need to take care in this sense. I believe, so my feeling is that all the devices, all the fabrication flow that I presented here could be easily done also in a non-clean room environment. And I'm pretty sure that it would be feasible. Clearly, you need vacuum-based systems. So you need, for example, evaporators. You need, in my case, the ALD, so the atomic layer deposition tool, and so on. If you would like to further reduce the cost, so even the establishment of a laboratory and equipment and stuff like this, there are clearly other techniques. So rather than going for vacuum based, you can even move, for example, to printing technology, which is one of the big advantage with respect to all the vacuum based technology. So the equipment are much cheaper, the maintenance it's cheaper, and you can definitely use them in clean room, in a non-clean room environment. So it's absolutely compatible. There are, for example, what I presented at the end, this laser approach. Sorry. Let me see that, for example, this laser approach here that I presented you on this paper substrate, you know, people have done, you know, strain sensor, biosensor, a lot of different devices, and they didn't even need to use any clean room. They just use this very cheap laser system. It's a system, you know, that you might find in workshop to cut or engrave plastic or materials in general. and you might have laser systems that go from 200 euro up to 2, 3, 5K maybe, and they don't need any clean room facility, and you can definitely still get, for example, this carbonized layer on substrates, on flexible substrate. So my suggestion is to really check the technologies which are available, consider also your budget and what are your capability, and I'm sure that according to the budget and the goal that you would like to achieve, you will definitely find a solution.
Thank you, sir.
So
I don't.
can I ask a question, please?
Sorry?
Can I have a question?
Yes, you can, please.
Professor Cantarella, thank you for a very wonderful talk. That was very informative. I have a couple of questions. First one is, you are using flexible substrates. There are either polymers or plastic substrates, right? So other than the stretching and bending advantages, are there any other, why are you not using any kind of thin metal foils or other flexible glass substrates?
Absolutely, yes. I mean, you're perfectly right. There is a very broad variety in this sense, in the sense that in our, experience, in our group, let me just go back here. I mean, in our group, we work mainly with the substrate that I presented here. Let me just share again the screen. We just went mainly on this PDMS, this stretchable substrate and polyamide foil, but we also have other works on other substrates. Exactly as you said, we are not limited to this. Was just for for a sake of time. But for example, we have worked also in the past with ultra thin foils, which is also a very important topic within the field of flexible electronics, so substrates which are below 2 micrometers. So in this case, there are, for example, Parylene, or there is PEN, or different other foils, as you said, and there is clearly a lot of research ongoing also on flexible glass, also on metallic foils. Absolutely. So there are, in some cases, there are studies in which the substrate, as you said, the metallic foils has been employed just as a substrate, but in other studies has been employed as also as a metal, so as a contact. So there are also studies in which the substrate has a twofold job: the carrier, so supporting the electronics, but also um, an active functionality for the electronics functionality. So you are perfectly right. There are people working with rubbers and polyamide, but definitely there are a lot of other substrate. I think as long as chemistry can support in terms of innovation in this sense, everything can be tested.
Thank you, Professor. My second question was, this IGEZO, which you have fabricated as a semiconductor, so
Yeah.
they are by RF sputtering, right? So is it a single source sputtering, or is it multi-layer and you are...
That's a good point. Thank you for the question. No, what we have, well, even in this case, it depends a lot on the research group, because our group is just one of many groups working with this alloy. The way we deposit this one is by radio frequency sputtering. So we have a target of indium, gallium, zinc, oxygen 4. And we just do the standard sputtering with argon. That's it. Although I know that within the metal oxide family, there are a lot of other semiconductors in which people they either use, the target as it is, but sometimes they even, for example, use a flow of oxygen to create the oxygen concentration they want. So there is a lot of variety in this sense. But in our case, the semiconductor that we use is, it's a target commercially available. We sputter it by radio frequency and we use argon.
Thank you, Professor.
You're welcome.
Thanks.
Is there any more question from participants? Okay, if no further questions are there, then let's thank our eminent speaker. Thank you, Professor Cantarella, for an enlightening and entertaining session of today's. We are grateful for the time and efforts you took to share your thoughts and experience with our IEEE NTC community. Last but not least, I'd like to thank our sponsor, Diamond sponsor Fiber Vacuum, Platinum sponsor Jagate Corporation, and Silver sponsors Excel Instrument Product Technology, Optimized Solution, Streamline, and Mansa Technology. Thank you, all the participants, for patience listening and learning. Thank you all.
Thank you very much, you, for the invitation, for attending.
Thank you, Professor.
Thanks a lot for such an. Thank you.
Thank you, Professor.
Thank you very much. And let's keep in touch. It was a wonderful experience. Hope we can still get in touch and do other activities in this direction.
Sure, Professor. Physically, when we will organize some conference, we welcome to IIT Indore at India.
Absolutely. It would be a great pleasure. I mean, I think we already connected to each other on LinkedIn also,
Yes,
right?
Yes.
Exactly. So
actually, our group also working in this field, like Zurich-based heterostructure field transistor and flexible substrate-based 2D material sensors.
that's great. Okay, that's fantastic. These are very interesting topics.
Yes.
No, absolutely. I mean, I would love to keep in touch, if there are possibilities or other activities that would be wonderful. I mean, as I said, our group is pretty young, so we always look for, collaboration and, your institute, it's well known, so.
Sure. Thank you so much, bro.
Great. Okay. Is there anything else, some documents or any stuff that I might need to provide you?
No, sir.
Okay, that's great. Okay, great. Well, if nothing else is needed, thank you very much again for the invitation, and let's keep in touch.
Only we need to your address, Professor, maybe some memento from the IIT Indore and IEEE NTC.
Sure,
We will
sure.
share your address, so I will convey from, toward the mail.
Sure. Yes, you mean the home address, I suppose, so the university address, right?
Yes, Professor.
Sure. I can send it straight away, not a problem.
Thank you, Professor.
Great. Okay, good. So once again, thank you very much, and let's keep in touch.
Sure. Thank you.
Great.
Professor.
Take care. Bye. Thank you.
Bye.
Bye. Bye.